Hey everyone, so I just wanted to show you a little bit about how much fun we can have with limiting values, and you can really explore this idea with a whole bunch of different kinds of expressions. So what I want you to do as an exercise is to just come up with maybe 3 expressions, something that you've seen before in math class. So I'll give a couple of ideas. Maybe for my 3 that I come up with, I will choose sine of x. Maybe I choose some kind of polynomial that looks like x squared plus 2x plus 3. And then maybe we choose something that's a little crazy. Maybe we'll do like an absolute value of x, right? And what I want you to do is just form a quotient expression. So grab some 2 of these and make them into a fraction, compose them into a fraction. So we could write it like sine of x over x squared plus 2x plus 3. And then just consider what this is going to do, how it's going to behave as you run a value up towards the barrier of infinity, at positive infinity. So we can kind of think of this in a couple of different ways. So one way you could do it is you could use the idea of infinite values to kind of think about what's going to happen. So you could think about what's going to happen if we were to plug in some infinite value. I'll call it omega. So we're going to have sine of omega, which is some infinite value. And then we've got x squared, which is going to become omega squared. We've got plus 2 omega, and then plus 3. And think about what this might be, right? This is something that we're playing with, we've talked about before as being like the hyperreals. This isn't a real number. You can't actually plug in a real infinity. This is just us playing with the idea of if we could plug in a real number that was infinite, what would it be? Or a number at infinity, what would it be? And then we can just kind of think about what this expression might be. So one way to think about this is to say, okay, well, like sine of omega, what might that be? Well, sine would be a function that depends on an angle. Here our angle, we don't really know what an infinite angle is. That's some kind of very rapidly spinning around the unit circle. So I don't exactly know what that is, but I know maybe some details about it. It would have to be between 1 and -1. Right? So, okay, I've got a little bit of a boundary up there. This is going to be trapped on the top between 1 and -1. What about on the bottom? Well, omega squared plus 2 omega plus 3, that's definitely going to be a huge value. That's going to be an infinite value. I've got something that's very, very large. I'm adding something else that's very, very large to it. I'm adding 3, which is insignificant, but still, it's not going to have anything that's going to prevent the bottom from being huge. So you can think of this as being trapped between 1 over huge and -1 over huge. Well, if you have this value of -1 that's over an infinite value, that's going to be 0. We know that to be the equivalent of the real number 0, right? It's that standardizing that becomes that this is 0, and then this one over here would also have to be 0. So we've got some kind of result, whatever it is, that's going to be between 0 and 0. Then we know that that's just going to have to be 0 itself. There's only one value that's going to be between 0 and 0, and that's going to be 0. So this entire thing is going to be 0. And it just becomes a little bit of a thought experiment. You can think about plugging things in. You can think about what happens. This is actually something we're going to cover in a little bit. That's called the Squeeze Theorem. And it's this idea of just squeezing something between an upper and a lower bound to get that it can't be anything but our limit. Now, this can be difficult to see, so I want to show you another way that you can think about limiting values whenever you're making some of these, and that's by using graphs. Graphs can be a really useful tool, so let's switch over to that. So here I've got Desmos, and Desmos is just a free graphing software that you can access at any time. It's at desmos.com/calculator. And so let's try just plugging in and seeing what happens with the thing that I had before. So let's do sine of x divided by, and then I'll group everything on the denominator there. We said it was x squared, and then I think I had, what was it? X squared plus 2x plus 3. Put that in there, 2x plus 3. And then we'll just close this off. And we'll see what happens as this thing tracks towards the infinite boundary, right? Now, this is only going to graph real numbers because it's the only thing that we can graph in a coordinate plane, but we can look at what's happening as we run this thing forward all the way into bigger and bigger values, and we can see that what's happening is it's just hugging that x-axis. And the x-axis there is that value of 0, right? It's just getting closer and closer and closer. And it's not actually at any point on the x-axis. It's actually just got a little bit of a gap. But it's going to be really, really close. And so we can say that our limiting value, the only value that I could get close to as a result of running this thing up towards the infinite boundary, would be 0. Now, a really interesting thing to think about is what's going to happen if you were to flip this fraction. So let's explore that one. If I was to flip this one, then maybe I would look at if I was to flip this fraction and take a look at what might happen when you have x squared plus 2x plus 3 over sine of x, well, maybe this time I choose to explore it using limiting values. So let's consider what the limit's going to be. I know that the numerator is not going to have any limiting value, right? This is an expression that grows very, very quickly. And so it's going to just continue to grow up and up and up all the way until you get to infinity. So by taking the limiting value of the top, we have no limit on the top. And on the bottom, you get, again, that kind of and again, you get that kind of oscillating idea of it being undetermined, but somewhere between -1 and 1. So we'll just say, again, this is going to be some kind of limit, maybe L, if it exists. Well, if we have a large value that continues to grow without bounds on the top, and the bottom is always going to be something between -1 and 1, well, then we've got a situation of a growing function that is not being constrained. It's pretty easy to logic through then that the limiting value doesn't exist. There's not going to be a single value big enough to take care of that numerator. Now, again, this can sometimes be difficult to see, so let's go back and take a look at what would happen if we were to graph this, and then we can get a visual. So now we're going to do the exact same thing, except over here, I'm going to do a little bit of a shortcut, and that's that I could just raise this entire thing to the -1 power, right? And that's just going to invert the entire thing. And now let's see what happens. It seems like I've lost the graph, so I'm going to go back towards the origin. See if I can find it again. And as you get all the way back there, there we go. Now we've been able to find that expression. So we got it down here. Maybe I zoom out and I look for it. There it is up there. Oh, it looks like it kind of bounces up and down. So let's pull it out, and here we go. Now we get to see what happens as we're looking at this flipped version of our original problem. And it looks like if you keep zooming out more and more and more, it's kind of this alternating, it looks like the shape just keeps alternating from the positive to the negative, and it looks like you just keep growing, whether it's positive or negative. So we've got kind of this alternating idea. The sign is causing us to switch the sign SIGN. So the SIN is causing us to switch the SIGN, and the polynomial is causing this thing to grow very quickly. So again, we have a situation where the limit's not going to exist for two reasons. One, it's climbing really quickly, and the second reason being that it's just bouncing back and forth really quickly as well. So in your task, what you're going to be asked to do is you're going to be asked to just consider 3 different constructions that are just like what we did in our graph here. Find 3 examples of making a quotient from those, and then just see what happens as you run this limit out towards infinity, and play around with the idea. Create a flip grid that kind of explores what you did. Remember that you're welcome to do this work on a piece of paper, where you can just simply record your flip grid on your phone using the code that's in the top left-hand corner of the next slide. But this is a nice, fun way to just kind of play with what happens as you look at a limit of something that runs off towards the positive infinite barrier.